Hi, my name is Christian, and today I'll be going over the paper Explainable Artificial Intelligence and Interpretive Machine Learning for Agriculture. This is a research article that was written by Masahiro Ryo. This article, as the name says, it goes over the topic of how explainable AI can be employed in agriculture. So to use an example for that, let's say a researcher has a question and they want to predict the crop yield of corn. Once they get that question, they could employ a universe of models to actually make that prediction. It could use some simple models like a linear model. It could use they could use some complex models like a random forest or a deep neural network. Now, each of these models they vary in complexity. Something like a linear model, for instance, may be something that a stakeholder or a farmer can easily look at and understand how the results are forming in that model. But once you use more complex models like a random forest or a deep neural network, that understanding of what's going on and how the variables are making a prediction, that's way more complex in those. Now, the research question in the paper, it evaluates basically a technique that's employed in agriculture, which is named tillage. So tillage is basically it means there is a drainage system in the soil. So it removes all that excess water, and that accelerates the crop growth, and it allows the soil to be aerated. Now, when there is no tillage, well, that means there is no drainage system. Now, the conventional wisdom before this paper was written is that no tillage, on average, reduces crop yield on maize by 7%. Now, this paper will say that yes, on average, it does reduce maize yield. However, it explores whether no tillage can increase yield if a certain condition is met. So this is the main question that the paper tries to explore. Now, the approach that the paper uses, it looks at this global maize crop yield data set, and then it runs 4 different machine learning algorithms to evaluate the research question. And then what's highlighted in green, that's when it uses interpretive machine learning to actually look at its results. So this would be like the most important part of the paper. That's where many of the findings of the paper emerge from, essentially. So one of the examples could be variable importance. So it looks at all the different variables that the data set has, and it ranks them on which ones are more important in predicting the crop yield versus which ones are least important in doing so. It also uses partial dependence. So this method helps visualize the association between a subset of predictors and their response while accounting for the average effect of those predictors. Now, by using all of these XAI methods, it comes up with novel discoveries, which we'll look into next. So by looking into partial dependence, for example, the paper found out that the crop yield is higher when the conventional tillage is lower than 5,000, and the maximum temperature for that data point is higher than 32 degrees Celsius. So the charts on the right will display that how the yield with conventional tillage and temperature interact with one another for the result. Also, by looking at the interaction importance, the paper found out that the yield with conventional tillage and temperature typically will have quite a strong interaction effect on the crop yield itself. So we can see how that interaction strength is displayed in each of the models on the right with the circle over that specific interaction variable. Now, this, in summary, helps highlight how XAI can be used to come up with novel discoveries and research. In this example, the domain was agriculture, but in many other examples, these techniques are also transferable.